Welcome to this presentation on melos-rs, Architectural Anatomy. Today we will explore the structural foundations of this project by deconstructing the Gang of Four design patterns that power this high-performance Rust CLI. This analysis serves as a deep dive into Pastel Sketchbook/melos-rs repository, examining how classic software engineering principles are applied within a modern systems programming context. Let's examine the performance proposition of melos-rs compared to its Dart-based predecessor. The metrics clearly illustrate a monumental shift in efficiency. For instance, execution time for the list command drops from 518 milliseconds to a mere 7.6 milliseconds. This represents an incredible 68x speedup. Furthermore, the exec command execution time is reduced from 555 milliseconds to 29 milliseconds, a 19x improvement. While switching to Rust is a key factor, this level of performance is also the result of structured architectural patterns designed specifically to facilitate more efficient execution. Encapsulating intent through the command pattern allows us to treat requests as first-class objects. By doing so, we effectively decouple the invoker from the logic that performs the action, which is a fundamental principle in maintaining a clean and scalable architecture. In the context of Pastel's technical anatomy, this is implemented within the src/commands module. As shown in the diagram, operations such as clean, run, publish, and exec exist as self-contained units. This structural isolation ensures that each behavior is separated from the CLI entry point, facilitating easier testing, maintenance, and the modular addition of new functionality without increasing system complexity. The facade pattern is fundamentally about creating a unified front by providing a simplified interface to a complex underlying system. In the context of our application, main.rs and cli.rs serve as this facade. By leveraging clap definitions, these modules offer a clean and intuitive API, such as the melos-rs bootstrap command. This approach intentionally masks the intricate operations happening beneath the surface, including complex workspace loading, sophisticated argument parsing, and the detailed merging of various configurations. By abstracting these background processes, we provide the user with a streamlined experience without requiring them to manage or even see the underlying complexity. The builder pattern is a cornerstone of our architecture for constructing state, specifically within the configuration module located in src config.mod. By definition, this pattern separates the intricate construction of a complex object from its final representation, providing a clean and modular approach to assembly. In our specific application, the necessity for this pattern arises from the requirement to merge multiple, diverse inputs into a single, valid configuration state. As illustrated, we must consolidate data from melos.yaml in its 6.x format and pubspec.yaml in its 7.x format, while also integrating dynamic inputs, such as CLI flags and environment variables. The configuration module serves as the builder, systematically merging these distinct sources to create a unified context. This entire process is completed before execution begins, ensuring that the application operates on a consistent, validated, and fully realized state throughout its lifecycle. The composite pattern allows us to create a uniform hierarchy by composing objects into tree structures that represent part-whole relationships. In our implementation, specifically within source/workspace.rs and the source/package directory, we utilize this pattern to manage our codebase effectively. The workspace entity functions as the root of the tree, encompassing multiple package entities as its branches and leaves. The primary advantage of this approach is that operations such as running tests or performing a version bump can be applied interchangeably to a single leaf node or the entire composite tree. By using identical logic for both individual packages and the workspace as a whole, we simplify our internal processes and ensure consistency across the entire system. Refining selection in our architecture is built upon the chain of responsibility design pattern located within src/filter.rs. This pattern operates by passing a request through a series of handlers, each tasked with either processing the request or passing it to the next link in the chain. In this specific application, when executing a list command, the package set travels through a chain of filters. Each filter step, such as applying the scope, ignore, or no private flags, systematically reduces the dataset based on predefined criteria. As illustrated by the cascading funnels, the data is refined at every stage, ensuring that the final output is precise and tailored to the user's requirements. This approach decouples the selection logic, making it easier to maintain and extend as new filtering rules are added. The adopter pattern serves as a fundamental bridge between disparate languages and systems. As implemented in our package module, this pattern allows incompatible interfaces to work together by acting as a translation layer. In this specific context, the tool is required to parse external Dart configurations. The adapter transforms these external schemas, including complex dependency definitions and semantic versions, into internal Rust structs that are compatible with our execution engine. As illustrated in the diagram, the adapter acts as the intermediary, mapping the square interface of the Dart configuration to the triangle interface required by our internal Rust logic, ensuring seamless data flow and architectural integrity. Interchangeable execution is achieved through the strategy pattern, a design approach that defines a family of algorithms, encapsulates each one, and makes them interchangeable. As implemented in the source file src/runner/mod.rs, this pattern allows the algorithm to vary independently from the clients that use it. In this application, the runner supports multiple execution strategies based on specific configuration flags. By utilizing flags like --order appendance or --concurrency, the tool can seamlessly swap between topological sorting for dependency management and concurrent execution for parallel processing. The visual diagram illustrates this flow. Starting from a single point, the system can diverge into path A for concurrent processing or path B for topological ordering. Crucially, the core task logic remains consistent across both strategies, with both paths eventually converging at the execution complete stage. This architecture ensures that the execution engine remains highly flexible and modular without requiring changes to the underlying tasks being performed. Let's examine how the observer pattern serves as a foundational element of our reactive system, specifically within the watcher module found in src/watcher/mod.rs. This pattern functions as a subscription mechanism, allowing the system to notify multiple objects whenever a specific event occurs within an observed object. In the context of this project, we apply the observer pattern to implement the --watch flag. The watcher module acts as a subscriber to file system events. As depicted in the technical anatomy diagram, whenever a file system change is detected, the watcher perceives this event and immediately notifies the runner. This notification serves as a trigger to rerun the command sequence automatically, ensuring that the system remains synchronized with the latest code changes without manual intervention. In this section, we will explore how the template method pattern is used to define skeletal structures for our operations. As implemented in our source code, this pattern allows us to define the overarching structure of an algorithm while deferring specific implementation steps to subclasses or external configurations. Practically, we apply this by using named scripts within the melos.yaml file to act as templates. These templates outline the necessary steps and environment variables required for a task. During execution, the system takes the skeleton and fills in the specific details based on the runtime context. For example, it injects dynamic variables such as melos_package name, allowing a single template to function correctly across various package environments without needing unique scripts for every individual case. Lifecycle management in our system is driven by the state pattern, a design principle that enables an object to alter its behavior in response to changes in its internal state. We see this pattern applied directly within the bootstrap and version commands. Packages transition through a defined lifecycle, as illustrated by the diagram. Starting from a dirty or unlinked state, the bootstrap command initiates a critical shift. By linking packages and executing pub/get, the workspace is transformed from a generic file tree into a structured, linked graph. This transition to a clean or linked state fundamentally changes the underlying interaction model of the CLI. From there, the system moves into a version state, completing the cycle. This structured approach ensures the CLI dynamically adapts its operations based on the current structural integrity and version status of the workspace. The core of our performance gains lies in an architecture specifically designed for speed through decoupling. By implementing the command pattern to isolate individual tasks and the strategy pattern to manage concurrency, melos-rs effectively eliminates the overhead inherent in monolithic execution models. As illustrated, our framework leverages key design patterns, including strategy, observer, and composite, to create a highly modular system. This structural clarity allows us to fully harness Rust's raw performance capabilities, ultimately delivering a 69-fold speedup in list generation. The contributor facade is a concept rooted in the use of a task file.yml to streamline project contributions. At its core, the goal is to reduce cognitive load by abstracting away the technical complexities inherent in a project's build and verification processes. In this application, a task file is utilized to simplify multifaceted Rust workflows. Rather than burdening contributors with complex command chains for formatting, linting, and testing, these actions are encapsulated into a single intuitive command, task check all. Benchmarking processes are similarly condensed into task bench all. By providing this standardized toolbox, we enable developers to perform comprehensive checks and performance measurements with minimal friction, ensuring a more efficient and accessible contribution environment. Examining the architectural foundation of melos-rs, we see a strategic application of 9 core Gang of 4 design patterns. Starting with the top row, the hub utilizes the command pattern to encapsulate requests as objects, while the mask provides a facade for simplifying complex subsystem interactions. The stack implements the builder pattern, allowing for the step-by-step construction of sophisticated objects. Moving to the middle row, the system's structural organization relies on the tree, which uses the composite pattern to manage part-whole hierarchies. The funnel employs a chain of responsibility to pass requests along a series of potential handlers, and the plug uses the adapter pattern to ensure that incompatible interfaces can work together seamlessly. In the final row, we look at behavioral logic. The path leverages the strategy pattern to define a family of interchangeable algorithms. The eye acts as an observer to monitor and react to state changes across the system, and the traffic light uses the state pattern to allow objects to alter their behavior as their internal state changes. Ultimately, this rigorous architectural approach, paired with the inherent performance and safety of the Rust language, results in a robust framework for next-generation tooling.